Excited to have Scott Lee here, who will be talking to us about composite manufacturing, stress analysis for honeycomb composite bonded joints, bonded panels. Scott has tremendous experience in a lot of different aircraft systems. He's worked for a large number of companies, so his experience base is going to help us understand how the design of these systems are implemented into operational programs. With that, over to you, Scott. Thanks for calling in and guiding us and teaching us. Over to you,
Okay.
Scott.
All right. Thanks, Vinay. Thanks for this invitation and thanks for having me. And I hope you all enjoy this presentation. It's going to be around 30 to 45 minutes. It's not too long. It's about 24 slides. So we'll get started. The title is Composite Manufacturing and Stress Analysis for Honeycomb Composite Bond Panels. What you see here is a picture of a nacelle with the thrust reverser and the fan cowls opened up. It's hinged and it's open. And then also, obviously, you see the engine inside as well. So just a quick introduction about myself. I went to UCLA, USC, took Vinay's courses in FEM, aircraft structures, composites, and fatigue. So I know Vinay very well, took a lot of his classes. I've been in the aerospace industry for about 13 years, mainly focusing on structural analysis and stress analysis. I specialize in finite element software, particularly FEMAT, to perform structural analysis simulations for aircrafts and spaceships. My current employer is Virgin Galactic. I'm part of the internal loads modeling team for the Delta program, and I currently reside in Dallas, Texas. These are some of the various companies I've worked for, as you can see down here. And yeah, so I've moved around quite a bit to a lot of different companies, have a wide range of experience working on different platforms, but the base fundamentals of structural analysis are the same. So if you have the base fundamentals down, then you can apply that to any company and any type of project, right? P over A plus MC over I is the same at any company you work, because that's just the fundamental physics, right? So yeah, like I said, I've worked at different companies, different platforms, and yeah. So presentation overview. In this presentation, what I'll be going over is the nacelle architecture overview. I'll be going over the manufacturing of composite bond panels. I'll be going over the detailed stress analysis for composite bond panels. And then I can take questions at the end. But if you guys have any questions, feel free to interrupt me anytime. I forgot one thing before I move on. One of these companies I used to work for is Raytheon Technologies. Before that, before they merged, it was Raytheon, and other company was called UTC Aerospace Systems, or United Technologies Corporation. I used to work at United Technologies Corporation in Riverside, California, about 7 years ago. I was there for 2 years, and it was a manufacturing facility that develops honeycomb composite bond panels. So this presentation was developed based off my experience working there. And I've given this presentation a couple times already to Vinay's students. He did invite me to come out again to speak with you guys this year. So I'm reusing what I've created in the past, but just kind of giving you guys some context of my experience and background. Why I developed this presentation was just from my experience back at United Technologies Corporation about 7 years ago. Sorry, one second. I'm going to close the door really fast. All right. This figure that you see on the bottom right is an exploded view of the various assemblies that make up the 787. In particular, what we want to focus on is the nacelle, circled in red. The nacelle is the outer encasing that covers the engine. Typically, it's underneath the wing, but in general, it's typically underneath the wing. But if other aircraft platforms, you sometimes see it on the horizontal or the vertical stabilizer back here. But yeah, that's what we're going to focus on, is the nacelle and the engine. Before I go into specific details of the nacelle and the engine, I want to first go over like the fundamental physics of the 4 forces of flight. As you guys are mostly aware, and this is, obviously fundamental and basic, the 4 forces of flight on an aircraft is lift. By the way, can you guys see my mouse when I move it?
Yeah, it looks good.
Yeah, you guys can see my mouse? Okay. All right. So you have lift, which is typically generated along the wings, right? You have drag, which is the resistance of most aerodynamic motion. And you have weight, which is the gravitational pull of the aircraft towards the center of the earth. And then you have the 4th force of flight, which is what we're going to focus on, is the forward thrust, which is generated by the engine and the nacelle. The engine and nacelle is basically a power plant that generates thrust. Let's just go back to fundamental physics, Newton's 3rd law. For every action, there is a reaction, right? So the nacelle and the engine, it generates thrust by sucking, I'll go over this in the next slide in more detail, but it's basically generating airflow and pushing it aft. Aft is this direction towards the right. And if it generates a large amount of force and flow in the aft direction, what is that going to do to the aircraft? It's going to push it forward, right? So that's what I mean by forward thrust. I know that's like fundamental, but I just wanted to go over that before I go on to the next slide. So the nacelle functionality and architecture. As I mentioned already, nacelles provide forward thrust. It maximizes thrust. Not only that, it absorbs engine noise, acoustic attenuation. So we need to minimize noise as much as possible over public areas, right? So the nacelle helps absorb some of that engine noise. I'll go over that in some later slides as well. And then the nacelle also provides engine access at the fan cowls and thrust reversers. As I showed in my first slide, the fan cowl and thrust reverser, as shown here, it's hinged. It opens up. Think of a hood of a car, right? Of an internal combustion engine car. If you want access to the engine bay, you need to open up the hood, right? Same thing with an aircraft. You need to, if you want to get access to the engine, you need to be able to open it up, right? Because the engine requires a lot of maintenance because the engine consists of so many dynamic moving parts. Things are going to fail and break. And so they need to go in there and maintain the engine, right? So the fan cowl and thrust reverser, you're able to open it up, as you saw in the first picture, to get access to the engine. The figure on the bottom left, it shows a cross-sectional view of the nacelle and the engine, just a general overview of the various components. And then the figure on the bottom right shows an exploded view of all the nacelle assemblies. We have the inlet cowl, the fan cowl, the thrust reverser, the pylon, exhaust cone, exhaust nozzle, and the engine itself. So as I mentioned, the engine plus nacelle work together as a power plant. So let's kind of walk through this slide. What you see here is a cross-sectional cut of a nacelle and an engine looking down, okay? So what happens from left to right? The engine sucks in a large volume of air through the fan is rotating at a high rotational velocity, sucking in a huge amount of air volume, right? 15% of the air enters the core, which is this middle region here, and that air is compressed to 40 times atmospheric pressure. The remaining 85% of the air bypasses the core and flows through the bypass duct. So what does that mean? A lot of the airflow actually doesn't go through the core compartment. It actually flows through the bypass zone, the bypass area, which is this purple area that you see here and here. It's a bypass duct. So a lot of the air actually, like I said, doesn't go through the core. Most of it goes through the bypass duct. But in the core, whatever air, the 50% of air that goes into the core, in the combustion chamber in the core, fuel is mixed with air and is burned at about 1500 degrees Celsius. This hot gas expands through the turbine to drive the fan and the compressor. And then the exhaust gas coming out of the core, which is the red, as well as the bypass air, which is the purple, it exits through the nozzle to produce forward thrust. In addition to that, the nacelle also acts as a way to slow down the aircraft before landing. So if you're ever near the wing aisle seat and you're sitting along the window side of the row, take a look. And if you have a view of the nacelle before landing, take a look at it. What you'll see is at the side of the nacelle, which is a thrust reverser, it actually uses the bypass air to slow the aircraft during landing by translating the sleeve, which is this guy here. So originally it's closed, okay? But it actually, before landing, it opens up, as you can see here, which as it opens, it deploys these blocker doors, which is this guy here, where that blocker door is basically going to redirect the airflow and actually push it to the side and forward, not aft. So when it does that during landing, it's going to reduce the speed of the aircraft right before it's about to land. They do this because they don't want to put too much wear on the brakes. And so they use this functionality to help reduce the speed of the aircraft before landing. Any questions thus far before I continue?
Any questions? No questions, Scott.
Okay. So as we move on to the next topic, manufacturing of composite bond panels, what are the types of materials that are utilized? Honeycomb composite bond panels consist of core, which is either aluminum core or Nomex core, consists of carbon fiber, CFRP weaves, consists of structural foaming adhesive to splice the cores together, and then also consists of adhesives to bond the face sheets to the core, top and bottom, as you can see here. Obviously, the top layer of plies is not shown in this image. It's showing the components underneath, but these are the various components that make up a composite bond panel. So what are the carbon fiber material forms? You have plain weave, 8 harness, and unidirectional tape. Plain weave is basically fibers that go above and below, up and down. The fibers going in the opposite direction. So there's fibers going in the warp direction, and then there's fibers going in the fill direction. 8 harness is you have a fiber going underneath and then over like 7 and then underneath. Unidirectional is self-explanatory. It's just fibers flowing in one direction. Notice the thickness differences between the three. Harness is the thickest, plane weave is second thickest, and then unidirectional is typically the least thickest. What are some of the differences in terms of properties between each of these types of carbon fiber material forms? Plane weave, loss of some properties by fiber crimping relative to tape. That's not good, but that's just, I guess, the downside of a plane weave. Less surface fiber breakout from drilling, machining, or damage. That's good. Good thickness and strength optimization for minimum gauge structure, typically used in field regions of bond panels. So in a honeycomb composite bond panel, you'll see plane weave fabric used quite a bit across the bond panel. 8 harness fabric, less crimping relative to plane weave, generally a higher cost than plane weave, less layup time due to higher thickness, typically used for pad ups and as sacrificial material. Unidirectional tape, it's good for optimization of weight and strength for thicker gauge structure. Core in transverse direction, typically used with automated layup. So we went over the carbon fiber forms. Now let's go over the core is typically aluminum, but also I mentioned no mix. It's manufactured by stacking sheets of aluminum with strips of adhesive between the sheets. So in a certain direction, that's where the two sheets are interfacing. And that direction is called the ribbon direction. And then perpendicular to that is called the the ribbon direction is this direction here. And then the perpendicular direction is considered the transverse direction. The stiffness and strength are different between the two directions because the sheets are bonded only in the ribbon direction. So typically the ribbon direction will have higher stiffness and higher strength relative to the transverse. And then this is the honeycomb cell. Okay, so in one of the previous slides, I talked about acoustic attenuation, reducing the decibel noises in airports when airplanes fly over neighborhoods, right? You want to make sure that airplanes not making too much noise and causing too much, disturbances, right? So the skins are pre-cured to facilitate acoustic treatment. What does that mean? The skins are basically baked in the autoclave first, and then it's pulled out, and then it's treated with holes, perforated holes. Okay. The skin is perforated on only one side, not both sides. You don't want to perforate both sides. So this is an example of a honeycomb core. A flow side skin, which as you can see here is perforated, but this back layer skin on the other side of the core, it's impervious. There's no holes. You don't want holes on that side. The perforated holes are typically drilled through the skin by multiple different methods: sandblasting, laser, multi-head drill. The skin is perforated to help with absorbing sound energy and dissipating the energy as heat into the air. So basically, the reason why it's perforated is because the honeycomb core acts as an acoustic chamber. So the sound waves and sound energy, as it's flowing, the airflow is flowing through that side of the skin, will actually flow into the core itself and basically dissipate the sound energy. I'm not an acoustic expert, so that's like the best explanation I can give you. But just imagine sounds as waves, and it flows through the skin into the core chamber and kind of cancels out. That's the reason why they perforate the skin. I'll go into some more detail that when you perforate a skin, when you add holes to the skin, you're going to make it obviously weaker, right? So that's a trade-off that we have to make as design and analysis engineers, is what are the requirements are not just structural, right? There might be other requirements like decibel levels, right? And so if we are forced to reduce decibel levels, and this is the best way of doing it, then we as engineers, structural analysis engineers, need to figure out, okay, what is the reduced capability of this face sheet skin when there's multiple holes located across, right? So that's something that we need to take into account when we do our analysis. Okay, so how are the face sheets bonded to the core, right? You have the core and the face sheet, but you need to bond them together, right? So there's two methods. There are two types of adhesive film used to bond core to the face sheets. There is supported and unsupported adhesive. Supported adhesive has a fiberglass mat to hold the adhesive in place, which helps ensure sufficient bond. It is more durable and holds the bond line thickness constant. It is not used in acoustic areas as the fiberglass mat would block the acoustic holes, which is not what you want. So on the perforated skin side, what they typically use is the unsupported adhesive, which is adhesive without the fiberglass mat. So it is used where the acoustic treatment is applied, as the supported adhesive scrim will block the acoustic holes, as I mentioned. It requires reticulation, removal of center cell adhesive via heat. So as you can see here, this red line is the non-perforated surface, and it's using a supported adhesive, whereas this bottom region here is the perforated surface, and it's using the unsupported adhesive to bond the face sheet to the core. So another thing that we need to take into account as engineers is galvanic corrosion. So carbon and aluminum don't get along, but our honeycomb composite bond panel consists of an aluminum core and the face sheets are carbon, right? So they're going to be interfacing together, right? So typically, and that leads to corrosion that occurs, galvanic corrosion on the aluminum part. So in order to prevent that as much as possible, which is the degradation of the material, they add a fiberglass isolator ply between the face sheet and aluminum core used to prevent galvanic corrosion, as I mentioned. Supported adhesive can also be used as an alternate, particularly on the co-cured face sheet side, this face sheet that doesn't have the perforated holes. So here's like a cross-sectional view of the various components that make up the honeycomb core sandwich panel. If you start from the bottom up, we have a surface film, which is this green. These blacks are the pre-cured skin laminate. The orange is the fiberglass isolator ply, which is meant to be that barrier between the carbon fiber and the aluminum core. You have the adhesive to bond the face sheet to the core. You have the core itself, and then you have foaming adhesive to bond the cores together, because the cores are not, it's not just one big gigantic core, it's modularized cores. It's cores that are different shapes that you got to put together. So you have to like kind of glue them together. And so the foaming adhesive is the way you can glue cores together. And then the other side is the same thing. You have supported adhesive, fiberglass isolator ply, and the other side of the face sheet, the co-cure side of the face sheet. All right, nacelle composite bond panel manufacturing summary. So how do we go about creating this honeycomb composite bond panel? Okay, first thing, step 1, obtain a tooling surface. Step 2, hand layup of plain weave plies along the tooling surface for the pre-cured skin. Step 3, cure the pre-cured skin in an autoclave with high temperature and pressure. Step 4, perforate the skin after cure. So after it's cured, take out the skin, perforate it. As I mentioned, there's 3 methods. In this example, it's a multi-head drill that you can just basically puncture the skin with uniform sized holes. Then apply the unsupported adhesive to reticulate. Obtain that same tooling surface that we used from the beginning and place that perforated skin onto that tooling surface with the adhesive. Then lay up the core, the aluminum core on top of that. Then you splice the cores together, as I mentioned, using foaming adhesive. Place a supported adhesive layer on top of that core and then hand lay up the back skin, the other side of the other face sheet side, and lay it on. After that's done, put the entire bond panel assembly back into the autoclave, because the second step of the layups is not obviously cured, right? So it needs to get cured. So the pre-cured skin is basically getting cured twice, right? So go in there, cure it again, and then after it's done, trim it to proper surface contour tolerances. That's very high level. There's a lot more details associated with that, but just want to give you guys a high-level overview of the process that takes place to develop these bond panels. Any questions thus far?
There's a question, there's several questions here. Let's go with your question. Go ahead.
What's the thickness of your like aluminum core there that it's able to like bend generally?
So the question is, what's the thickness of the aluminum honeycomb that allows you to form it into a shape? Did I get it right?
Yeah.
The honeycomb core itself, what's the thickness?
Yeah.
So that varies depending on your application. Obviously, the thicker the core, the thicker, which is basically the height of the core. If it's bigger, it's good in a sense because your moment of inertia between the face sheets is growing, so it's much stiffer out of plane, much stiffer under bending. But if it becomes too thick, then it's more prone to possibly buckling under like flatwise compression, right? Because the core itself is quite thin and flimsy. So to answer your question, Vinay, you can correct me if I'm wrong, but I've seen it like, it depends on your application, 0.5 inches, 1 inch, 2 inch, you know.
Yeah. 2 inches on the high side.
Yeah.
Half inch is probably on the low side.
Yeah. Anywhere from a half inch to 2 inches. Yeah.
And then you had a question, go ahead.
Yeah, you can use Nomex over aluminum. Nomex is a higher temperature resistance, and aluminum is cheaper. Is that why you guys are using aluminum, or is like aluminum is stronger here?
So the question is, when you choose Nomex over aluminum honeycomb, or the other way around, is it a cost factor, is it a strength factor, or environment factor?
Yeah, that's a good question. Nomex is like a more of a like polymer type of material. I do believe that, I mean, Vinay, correct me if I'm wrong, it's probably lighter in weight relative to aluminum, but also weaker, I think. I think Nomex, they like to use it. I mean, don't quote me on this. They like to use it in regions where there's a high amount of like high amount of curvature because it's more flexible, I think. So anything with a high amount of curvature, they may prefer to use Nomex because it's a better application in those geometric areas versus aluminum. But don't quote me on that. I'm just kind of basing that off memory. In highly loaded regions, you want to use mostly aluminum because, like I said, Nomex is not as strong. Do you want to add to that, Vinay?
No, got it right.
Okay. Any other questions?
So you can proceed.
All right. So we just went over like how the composite bond panel gets manufactured, right? The steps and processes. But during those steps and processes, nothing ever works out perfectly. If you ever work at a manufacturing facility, things never go right. Especially with composites, it's a different ballgame as well. Composites are notoriously known to be hard to manufacture just due to lots of variability in the material itself, variability with how it's being baked in the autoclave, operator error, technician error. There's something called springback in composites, where as things are curing, a composite actually warps and deflects. So whatever you can imagine that can go wrong will go wrong, okay? And there's going to be defects that occur on the part. Because there's a defect, are we going to actually throw away a very expensive aerospace bond panel that probably costs anywhere, don't quote me on this, but like anywhere from $30,000 to $100,000 for one of these bond panel assemblies? Are you going to throw that away? And is the company going to eat up that cost? Obviously not, or else the company will go bankrupt, most likely. So what we need to do is we see these defects, we do quality inspection, and we know, hey, there's a dent there, there's delaminations there. Let's do some scans, A scans, do these NDI, non-destructive testing, non-destructive inspection techniques to determine on the inside if there's any defects, right? And then from a structural standpoint, when we see these defects, can we live with it from a structural perspective? Can we show it good analytically with a knockdown factor to the material allowables, reanalyzing the part with the defect, modeling it in. So that's what I did when I was working at United Technologies Corporation. But what I'm going to be going over are some of the defects, common ones that we typically see when we're manufacturing these. Delaminations due to impact damage, machine errors, as you can see here. Inside the laminate, it delaminates. There's a separation of the plies from one another along the matrix. Shear cracks, fiber failure. There's foreign object damage due to error by the operators. They forget to remove the plastic separator film before laying up the plies. There's wrinkles can occur due to improper layup of the ply. During the perforation of the holes, sometimes the machine screws up. And so sometimes the holes are not in tolerance. They're enlarged, they're oversized holes, not per the spec. Or the holes get cracked just due to machine error. Another issue is this bond between the face sheet and the core due to either air entrapment, presence of moisture, insufficient bonding pressure, or gaps between the core and the pre-cured face sheet. So basically the adhesive is not working here locally and the face sheet is no longer bonded to the core. Other types of defects. If you place a fastener through a honeycomb core and you torque it to preload the joint, if you preload it too much, you're going to crush the core. The core itself is very flimsy, so it could be misshaped cells, wrinkled cell walls, incorrect core height, buckled cell walls, as you see here. Dents on the laminate, that's a very common thing. Dents on panels due to dropping objects on the part, banging the part as it's being transported, not cleaning the tooling surface properly, therefore leaving an indentation during cure, gouges and scratches on face sheets due to impact from sharp objects. So there's other types of defects that can occur. These are just the common ones. So with that, how do we assess these defects from a structural analysis perspective, stress perspective? So what are some of the mechanical properties of composite laminates that we have to know and understand? We need to understand the ultimate strength, obviously. What is the elastic modulus? What is the stiffness of the lamina and the laminate? What is the pristine B basis lamina allowable as a function of temperature? As the temperature goes up, you start reaching the glass transition temperature of the prepreg epoxy, and therefore there is a reduction in the capability of your ply and your laminate as a higher temperature you go. BVID, C and OHT correction factors. BVID stands for barely visible impact damage. So imagine someone dropping a tool at a certain height that dents the part, what is the correction factor that you need to apply when that happens? What is the reduced capability in your laminate when that happens? Open hole tension. So just imagine some hole, 0.25 inches being drilled through the laminate. What is the reduced capability of your laminate when you have a hole versus without a hole, right? Perforated hole correction factors, kind of discussed that. The pre-cured skin, flow skin side is perforated for acoustic attenuation. So we need to understand what are the knockdown factors when we do that to the laminate. Unnotched properties, basically meaning a pure, pristine laminate without any defects, without any holes. Interlaminar shear, interlaminar tension. What is the capability between the plies, along the matrix, like in shear and tension? Flatwise tension properties of the adhesive. So what can happen sometimes is we need to know what the tension capability of the adhesive is between the fascia and the core. Shear properties of the adhesive for bonded lap joints. There's a lot of joints where they actually are bonded together, not bolted, and it's going to be bonded with some kind of adhesive, and we need to understand what is the shear capability of that adhesive and the joint overall. Fatigue no growth allowables. Fatigue is a different animal when you're dealing with composites versus metals. Much more complicated process. Some companies, they use very simplified approaches to determine what is the fatigue microstrain allowable of a laminate. But basically, it's just like a coalescence of multiple cracks that form together and then goes into one big crack. And then sooner or later, that one big crack will cause failure. But it's just basically micro crackings continuously growing across the matrix and the fibers. Laminate pull-through is basically, laminate pull-through is basically when you have like a fuselage skin, the fuselage skin will have countersunk fasteners that are drilled through the skin, which is then interfacing with another component inside the fuselage skin, like a frame or a fitting. And there can be sometimes a high out-of-plane load with respect to the skin, and the out-of-plane load will tug on the fastener head and pull through the laminate. It's a critical failure mode. Pull-off allowable. So in this example here, you have a fitting with a fastener with a face sheet that's bonded to the core. And if you have a high out-of-plane load, it's going to basically impose a out-of-plane load that's going to be imparted through the adhesive. So we need to know what is the tension pull-off capability of the adhesive. Core shear. So the core is going to be seeing transverse shear in two directions, the ribbon and transverse directions. So there's an interaction that occurs between both directions. What is the capability of the core? And then flatwise compression of the core. So under a curved part, and if there's a bending moment, it can actually impose like a flatwise compression, crushing the core. And so we got to check for that too. That was a lot there. Is there any questions on this slide?
Any questions about this slide? Go ahead. Continue. So a lot, in summary, a lot goes on in really substantiating the design of a system for an aircraft. Continue.
Yeah, lots of knowledge that you have to know and understand. Yeah. Okay, we're good to go, Vinay?
Yep. There's a question right now. Go ahead.
I really mentioned the last
I
don't know exact details, but just from a high level perspective, the matrix is pre-preg matrix. It gets cured, right? So it's a thermal set matrix, right? So it turns into like a plastic type of substance. But under high temperatures, that matrix starts to degrade and starts turning into more of a liquid. And once that starts to degrade, you start to lose like the bonding between the plies, and basically the overall strength of your laminate will decrease. So they typically, what they do is they do testing of laminates under various different temperature zones. And this is something that typically you needed to validate through test. You can't just analytically figure this out because it's a material property type of check. So typically around I don't remember the exact curve in it, but is it like maybe sort of like exponential decrease? It's not linear, I don't think.
So if you operate above the glass transition temperature, you precipitously decrease the strength of the system. And so you want to operate below the glass transition temperature so you can stay safe in operation.
Yeah.
Is that your glass transition temperature of your adhesive and your pre-preg?
Yeah, glass transition temperature of any of the polymers used. It could be rubber, it could be composites, adhesives. But I do think we should move to the next slide. Go ahead, Scott.
Okay. About
Great question.
5, 6 more slides.
Go ahead, take your time.
Okay.
I think folks are getting a lot out of this, right? Correct?
Okay. So in terms of like the nitty-gritty structural analysis substantiation, what we typically do is model the components in a finite element software. And then we use other types of software like Hypersizer to calculate our margins of safety. So in this example here, we mesh our components typically with 1-inch by 1-inch elements, shell elements. Typically you use 2D shell elements with p-comp property definitions that represent the honeycomb core layup, the plies and the core, and then the plies on the other side. You could also use 3D hex elements to represent the core and then model the face sheets with 2D shells on top and bottom of the 3D element. Typically, the first option is utilized the most because it's easier in terms of FEM modeling. After each component is meshed, they're attached together with C-bushes. C-bushes are just basically 6 degrees of freedom springs that are used to attach components together in finite element softwares. After you do that, you apply boundary condition because the component is as a static component, right? It's moving in the air, but under loading, it's static. It's a static analysis, right? We're not doing dynamic analysis. So you need to apply boundary conditions, typically at the pylon attachment to the wing. In terms of loading, it's typically pressure loading, core compartment pressure, external pressures, fan duct pressures, and then thermal loading, because as you can imagine, you're at the engine region, so you're going to see high temperatures as well. Models ran in Nacelles, which is a finite element solver, either linear static or nonlinear if there's gap elements that represent basically gapping between components that you want to model if they become in contact. Once the model is solved, you can extract running loads from your shell elements, NX, NY, NXY, MX, MXY, QX, QY. And then all of that can then be inputted into another software called Hypersizer, where it can start checking all these different failure modes, which I'll go over in the next slide, and calculating margins of safety and seeing if your design is structurally sound based off the loading and boundary condition. So Hypersizer is a program that checks different types of failure modes. So, some of which are shown here. Some are, a lot of these are obvious. Face sheet failure, where the face sheet ruptures. We talked about this flexural crushing of the core, so buckling of the core in the transverse direction. Transverse shear failure of the core at the ramp regions, at the ramp regions in the curvature zones. There's a flatwise tension and compression that you got to check for. Intracellular buckling, dimpling of the face sheets. There's general overall instability of the honeycomb sandwich panel as a whole. There is shear core instability as well. And then there's face sheet wrinkling. And on top of that, other things you got to check for are the joint failure modes, right? Because those parts are all connected to one another with fasteners. It's either bonded or fastened, mechanically fastened, right? And typically for composites, the critical failure mode is actually at the joints, okay? So the big things are pull through, as I mentioned before in the previous slides, where the countersunk head is pulling through the laminate under a high tension force, or bearing bypass. So as the parts are bearing along each other, bearing is a typical critical failure mode for composites as well. And then, there's these other types of failure modes which are not as critical typically. So in terms of analyzing some of these defects, like voids and dispawns, right? How do we go about analyzing that? Because the part is not per spec. There are non-conformances. So it's not per design, right? We don't want these dispawns on the part. How do we analyze this? How do we substantiate this, right? So one way of doing that is this person, Stephen Ward, he developed some closed form solutions to analyze these panels that are disbonded under compressive forces. Because imagine you have a panel, right? The face sheet, like down here, it's no longer supported by the core, right? So now that face sheet that's disbonded in a local area will be more prone to buckle out because now your buckling length has grown because it's no longer supported by the core because the adhesive is not bonding that face sheet to the core. So that area can buckle possibly. So that's something that we got to check. And typically you can use this closed form solution, but we don't like to typically, or I don't like to typically do that. What we typically do to get the most realistic answers is modeling it in a FEM. So here we have a FEM with 3D elements that represent the core. And then you have 2D shell elements that represent the face sheets. And then you mimic the disbond by disconnecting the nodes of the shells to the core elements. So they are not connected in the disbond zone. And then you run your FEM with the loads and you determine if that area of disbond is going to buckle under that load and boundary condition. And you determine the eigenvalue, buckling eigenvalue. What this slide is supposed to represent is that We use a FEM because the previous example, this paper, it's a closed form solution, so you can only idealize the boundary conditions of either like 100% simply supported or 100% fixed. Those are idealized boundary conditions, but in reality, when you look at the part itself, the boundary condition is neither of those. It's somewhere in between. And our FEM shows, relative to the analysis results from the paper, that indeed the FEM is in between the fixed and the simply supported, closer to the fixed actually. But that's what we want to see. If it was above or below, then we would know that our FEM has some kind of issues. But yeah, it's in between, which is good. Two more slides. So analysis of defects for dents is analyzed very simply. A dent is just analyzed as if it was an actual hole. That's conservative because a dent is not a hole, like the material is still there. But from a structural analysis perspective, we want to be conservative, so we analyze it as a whole. There's a paper here called Stress Fracture Criteria for Laminated Composites Containing Stress Concentrations. So as you guys are aware, when there are holes, there's going to be stress concentrations occurring near the edge of the holes. And so this paper kind of discusses that with equations based off the laminate effective properties, how to calculate the KTs. And then using those KTs, you can evaluate with the increased stress level due to the stress concentration, whether your part is going to fail or not due to this dent that's treated like a hole, basically. So yeah, that was basically it. Took about 1 hour. Yeah, in summary, what did we go over? We went over the nacelle functionality and architecture. We went over the engine plus nacelle is equal to a power plant. We went over the various materials utilized for a bond panel assembly. We went over some of the defects that occur during fabrication. We went over some of the mechanical properties of laminates, some of the critical failure modes of sandwich panels, and then how we analyzed these nonconformities. But yeah, that's my last slide, so I can take any questions.
Thank you, Scott. Any questions from here? Anybody here? Or on the line, please? Any questions? There is a question.
How do you check for defects within your composite panel, like specifically in the center of the?
Yeah, so the question on the classroom is composites, when you manufacture them, you can introduce defects during that process. And the question is how you find those defects, particularly in areas that are away from edges.
Yeah, so kind of briefly went over this, but these companies have what they call like NDIs. NDI stands for non-destructive inspection techniques. So C scans, A scans. So basically it's these types of scanning materials that's able to actually look inside the honeycomb composite bond panel, not just the surface, but even inside. It uses, Vinay, maybe you could explain this better than me, but they use like these various tools that like, Vinay, is it sound waves?
Yeah, so there's several techniques. One is thermography, using heat. And if you have a defect, the heat will not be able to penetrate in the same way if there's no defect. So that will allow you to understand where a defect exists. Another one is called shearography. It uses visual fields to understand surface deformations due to a defect being present. And you know what that looks like without the defect being present. So therefore, you will know whether a defect is present. A third approach typically used is called ultrasound, where you send a sound wave and there's a defect, it's going to bounce back quickly. If there's no defect, it's going to keep going, which means it will take longer for the signal to return. So that way you can differentiate between a defect and non-defective panel. There's also other techniques like eddy currents, X-ray, and other techniques exist to do this kind of work. But ultrasound is the most preferred option. Any other questions here before we continue? There's another question.
I feel like you might have talked about it, but how do you incorporate like some of those defects into your FEM model, like something like delamination or like wrinkling? Is there just like tools that you just like add to it, or are you like straight catting some of the defects into it?
Yeah, so the question, Scott, and I think you did cover it, but see if you can connect the dots a bit more. And is how to incorporate those kinds of defects into your final elements. And I think you did cover a little bit that when you cover testing, open hole allowable, but also when you covered that eigenvalue example. Can you kind of connect the dots there quickly there?
Excuse me. So when we do testing on the laminate, they actually damage the laminate, BVID, barely visible impact damage, or open hole tension. So we actually just drill a hole, 0.25-inch diameter hole, and then we test it to determine, okay, what is the reduced capability of the laminate due to this damage? And typically we use that allowable to compare against our stress levels to account for these defects. So we're not actually modeling it in the FEM, but in certain instances, like I mentioned in one of the previous slides, is in some instances we actually do model it, where for this bond, we basically, the shell elements and the 3D hex element, it's not the nodes are not equivalents. They are separate nodes. They are not joined together. And that's how we model the disk bonds.
Thanks, Scott. I think there's no further questions here. I want to thank you for your talk.
Okay, no problem.
And thanks for making time. I know it's late where you are at, but I always appreciate the talk from you. So thanks for your time. Appreciate it.
Yeah, no problem. Thanks for having me, guys. Thanks, Vinay. Appreciate it.
Thank you. It's exciting. Thank you.
Okay.
Okay, so thank you, Scott. So with that, we're going to go to today's lecture.